Good morning. So our topic is web-based system for detecting plant leaf disease and providing treatment recommendation. So we are a group of six with the team members of Maithili S, Paushya S, Kalaimani M, Srivatsla R, Lakshmi SR, and Logesh Surya. So our topic is to explain about our topic. Plant disease persistently challenge farmers, affecting their income and food production. Even experts in the field find it difficult to contain the spread of these diseases once they take hold within a plant. While experts can smallholders and diagnose the elements through close inspection of affected areas. Smallholder farmers, who constitute a significant portion of the population, often lack access to such expertise. There's a need for an effective approach to identify plant leaf disease and access their stages. Owing to the ongoing internet revolution and advancement in computer vision models, the agriculture sectors can now harness computer vision technique. CNN stands out as the most advanced approach for image classification, offering precise diagnosis. Their proposal leverages a deep learning module developed through transfer learning to diagnose plant disease via web-based application. We also have a pre-trained model which is created using images of diverse plant leaves from the plant village dataset, enabling the identification and diagnosis of disease. To gauge the effectiveness of this approach, various performance metrics such as precision, recall, F1 score, and accuracy were computed and continuously monitored. The proposal achieved an impressive accuracy rate of nearly 95% with the ResNet model and plant village dataset. The initiative has the potential to revolutionize farming practices and bolster food production. So, coming to our introduction, as the global population grows, the demand for agriculture product rises. Plant disease cause operational and financial challenges in agronomy, responsible for at least 10% of global food supply losses. Early detection in vital in total agriculture sector with Africa and Asia as major producers, mainly small-scale family farmers. Traditional human-based crop disease categorization is no longer feasible. Deep learning, especially CNN, is the most promising method for automated decision making and discrimination. Disease detection and prescription module's primary goal is to provide vital information and alerts about crop damaging and leaf diseases. Users can capture real-time plant leaf images or use stored ones to match with a predefined trained model, receiving relevant results to prevent diseases and enhance yield. So deep learning has improved attributive extraction and identification accuracy in plant disease diagnosis.
So the proposed methodology is real-time scanner. Upon website entry, users are immediately presented with a real-time scanning option prominently featured on the homepage. This functionality eliminates the need for users to navigate the process of capturing and storing photos before initiating analysis. Real-time scanners harness the device's camera, accessible directly through the web browser, simplifying the entire procedure. This ensures swift results delivery, eliminating the manual, simplifying the handling of the image files. Leveraging the video element, the technology seamlessly accesses the device's camera via the web browser. The captured image is previewed using the Canva element, allowing users to access its quality before commencing disease detection, thereby identifying any potential issue. From local device. In some cases where internet connectivity may be unreliable or where users prefer to analyze pre-captured images, an option exists to select image stored locally. Users can effortlessly upload leaf image from their local storage, rendering it a convenient choice for offline usage or for analyzing image captured at different time. Similarly, to a real-time scanning option, users receive a preview of their chosen image before initiating the disease detection process. This precautionary step minimizes errors, ensuring the delivery of precise result. This approach caters to both real-time scanning and image selection from local storage, providing users with flexibility and convenience. The inclusion of image previews prior to analysis serve to enhance the user's experience, mitigating the possibility of inaccuracy resulting from poorly captured image.
Okay. The model used here is CNN model. The algorithmic representation of CNN for plant leaf disease detection can be summarized as localized featureized learning, which utilizes CNN automatically detect localized features in input images. Hierarchical pattern recognition is also done using it. Translation invariance, effective handling of variations can be done, effectively handling minor variations in the positioning, angles, and orientation of objects within images. It also helps in ideal of varied leaf presentations, which has the capability is especially valuable for identifying diseases in leaves presented from different angles and orientation. It also reduces the parameter count, where CNS employ parameter sharing and pooling layers to reduce the total number of model parameters, prevent overfitting, which also helps the risk of mitigating by making the model more robust and computationally efficient. It also helps in lowering the parameter count, accelerating both model training and prediction process. It also have end-to-end learning, which helps in comprehensive model optimization and also helps in task relevances. This feature empowers the model to learn the most permanent characteristics of specific tasks such as plant leaf disease. So ResNet here. So about ResNet, it profoundly uses CNN, boosting 50 layers. Its architecture seamlessly integrates residential connections, conventional and pooling layers, and are fully connected layers. The structures encompass four fundamental blocks, each with a unique layer composition. The starting convection block consists of a convolution layer, followed by max pooling. Following are three residual blocks, each housing layer equipped with residual connections, compromising conventional layers, both normalization layers and ReLU activation functions. In parallel, the identify block mirroring the residual block establish a direct input-output connection, bypassing the initial convolution layer. The last layer is fully connected layer which utilizes a softmax activation function to generate the probability distribution for different classes. Concluding the architecture. It also helps in a deep residual network as distinguished class of conventional neural network categorized by intrinsic 50-layer depth. This model processes substantial computational power amounting to 3.8 to 10 power 9 floating point operations. It also helps in subtype of ANNS construct this network by stacking residual block. This model utilizes the ImageNet 2012 dataset comprising 10,000 listing image classes involving 1.28 million images for model training and an additional of 50,000 for validation. The evaluation of 1 crore equating to a significant 3.8 billion floating point operations, using a notable enhancement by incorporating three layers, bottleneck blocks differing from prior models, two-layer configuration. It also helps in 50 layers utilize a 64 conventional kernel size at 7 to 7 and a stride of initial layer hosting 1,000 nodes and operating through full connectivity, which employs a software activation function for data categorization. The organized configuration of the 50 layers arranged in distinct identical blocks with varying kernel sizes and layer counts effectively mitigates the varnishing gradient problem encountered in extremely deep neural network. So coming to the conclusion, plant disease pose a significant global agricultural challenge, threatening food production and causing crop losses. Automated disease detection in plants, particularly using CNN, is crucial for agricultural advancement. Farmers struggling with manual disease identification, emphasizing the need for adaptable automated solution. Limited annotated datasets have hindered the widespread adoption of deep learning models. The proposal introduced a real-time scanning for quick disease identification, offering essential disease information. The model achieves 95% accuracy, enabling early detection. Food security is prioritized with potential for diverse image processing techniques. Integration with chat platforms like WhatsApp enhance accessibility, exploring alternative models and accessing disease severity improve effectiveness. Advanced algorithms analyze environmental factors, providing personal recommendations. AR aids visualization and real-time advice. Machine learning predicts outbreaks, suggested proactive solutions. These enhancements develop plant health management for sustainable agriculture. Thanking you. And our paper ID is 128. We are very happy to convey our paper. Thank you.